We're moving now to the last two talks of this session before the lunch break, and we're starting with Natasha Niessen. She's doing an industry PhD with General Electric and the Technical University in Munich, and she's going to be talking about implicit neural representation in multi-contrast MRI reconstruction.
Yeah, so thank you very much already for the kind introduction. I'm very honored to present today our work INR meets multi-contrast MRI reconstruction that we have published in a MICAI workshop on reconstruction in motion estimation last year. So first of all, I want to introduce briefly multi-contrast MRI. So in multi-contrast MRI, multiple image contrasts are acquired within a single scan. And each of these contrast images reflect a varying MR experimental parameter, for example, inversion time short TI or echo time short TE. And these images can be used then, for example, for quantitative parameter fitting. So we can see in the first row that by varying the inversion time short TI, we can then estimate the quantitative parameter T1 by fitting an inversion recovery curve. And then in the second row, we can see that the multi-echo images, so similar to the first, that was actually the data that the first method that Julia just introduced is using. And this can be used, as you already heard, to fit quantitative T2 star maps. And these contrast images for the varying echo times follow a decay curve. However, this kind of sequences suffers from usually very long scan times, and so this limits the clinical adoption of multi-contrast MRI. For example, the 10 inversion time images you can see in the first row took 22 minutes to acquire. We propose a method with which we can reduce the scan time down to 3 minutes 25 only, and our method is only scan-specific and self-supervised, which means that no training data is required. Now, before going into detail, I want to give a brief overview of our method. Our method combines an advanced acquisition strategy and a deep learning-based reconstruction. And for the acquisition part, we propose to use complementary undersampling across contrasts. And for the reconstruction, we propose a joint INR reconstruction framework that uses this complementary information that was acquired for the different contrasts. And this method is actually based on the observation that if you look at these different contrast images, the contrast changes among these images, but the anatomy of the object being scanned, so in this case the brain, remains constant. And so let's dive a little bit deeper into the complementary undersampling part. So as you have heard before today, and as you probably know, in MRI we measure the data in a frequency space that we call K-space. And the contrast information and the anatomical detail information is actually contained in different parts of K-space. So the contrast information is contained in the low frequency part, so here visualized in blue, and the anatomical details and higher frequency information is in the outer parts of K-space. And so this means to accelerate multi-contrast MRI sequences, what we do is that we sample the K-space center densely to actually have the contrast information for all the different contrasts. And then for the higher frequencies, we can actually sample more sparsely and complementary across contrasts. With complementary, I mean that if a K-space point is sampled, for example, in the mask for TI1, and then this point is less likely to be sampled in the undersampling masks. Now, in order to use this complementary acquired data, we have to reconstruct the data jointly. And the way we do this is with an implicit neural representation network, and you can here see different training epochs. And now I'm going to go into more detail how this works. So in general, implicit neural representation is a deep learning architecture that learns a continuous mapping from the image coordinates, so in this case y and z, to the complex image intensity values. And we can look at this like an encoder-decoder architecture. And in our case, we use hash grid encoding. And this hash grid encoding actually ensures that we can also learn high frequency information, so like details in the image, because usually networks like MLPs would have a spectral bias towards low frequency, so we would just have kind of a blurred image. And additionally to this hash grid encoding, we use a very shallow MLP with just 2 layers and 64 neurons each. Now, in our case, we reconstruct not just one image at a time, but actually 10 contrast images jointly, which means that the output of the network is not just one image intensity per coordinate, but actually the 10 image coordinates for the different contrast images. And I want to highlight that our method is scan-specific and self-supervised. So this means that the network is only trained with the data acquired for one particular subject, and yeah, therefore is also less prone to hallucinations, as we have heard, as can happen in like supervised methods, as we heard before. Now I want to go into more detail how the network actually learns this representation. So at each epoch, we apply to the learned images the forward model, which in MRI consists in multiplying with the color sensitivity maps and also calculating the Fourier transform. And with this, we obtain what we call the learned K-space across different coils. And so now, in order to compare this learned K-space with the acquired data, we apply the complementary undersampling masks to have a data consistency loss in K-space. And we also use a distance weighting because in K-space you have higher intensities in the center of K-space. And so to kind of make sure that the lower intensities in the high frequency domain are also kind of respected. Okay, so now let's look at how we kind of evaluated our method. We evaluate this on an MPN-rich data set that we actually data that we acquired ourselves, and it's a multiple inversion time sequence. And we acquired 3D data. So before you saw Y and Z that were used to train the network. So this means we do the slice-wise, and the X direction is kind of the readout direction. And so this is really cool because that way you can kind of reconstruct different slices, but at the end you can stack the slices together and have a 3D volume of the brain. So also look at different, not just at axial views, but also sagittal and coronal views. And we acquired this on a 3 Tesla Discovery G healthcare scanner. And we'll now look at the scan times that we, with which we acquired data for these 10 inversion contrast images. So in MRI, as you heard before, there's also a trade-off between scan time and resolution. And so at a resolution of 1.5 millimeters, we acquired fully sampled data, which took 22 minutes. And then we also acquired undersampled, so accelerated data in 3 minutes 25, and this corresponds to an acceleration factor of 6. And at a 1 millimeter resolution, a fully sampled scan would, in theory, take 1 hour 45 minutes. But don't worry, we did not scan this in a volunteer because that would be far too long. And instead, we acquired a protocol in 4 minutes 22. And so this corresponds to an undersampling of R20. And as I mentioned before, the INR reconstruction was performed slice-wise. And for each slice, this reconstruction took around 1.2 seconds. And we keep the same hyperparameters across all slices and also all volunteers to show the generalizability of our method. And let's look at some results. So these are some results that we submitted to AIC and Alzheimer's conference recently. And here we're looking at the 1.5 millimeter resolution data because in this one we could scan a fully sampled data set, which allows us to have a reference. So the first row that you see here is coming from this fully sampled scan that took 22 minutes and is reconstructed with an inverse Fourier transform, which is kind of the model used for MRI. And you can see the 10 inversion contrast images, and then on the right you can see a quantitative T1 map that was fitted based on this data. Below we can see the undersampled data that was acquired in 3 minutes 25. And in the first row, you can, and below here you can see reference-based metrics, PSNR and SSAM. And when you look at the data, you can see that our joint INR reconstruction allows to reconstruct denoised images for all the contrasts and also corresponds to the reference image. The first method we compared it to, so now we look at different comparison methods, is subspace reconstruction, which is a conventional reconstruction method, so no deep learning, but it also reconstructs all images jointly, and so also takes advantage of the complementary undersampled data. And in general, the images look good regarding noise, but actually the denoising works less good for the first inversion time images, which is because these are harder to recover because the signal actually changes more in these contrasts. And below we can see PIX, which was mentioned before. Actually, is like a compressed sensing and parallel imaging method that reconstructs all the images individually. And there we can see that it's just noisy in general, and which can also be seen in the T1 map. And then last we compared it also to TD-DIP, which is time-dependent deep image prior, so a deep learning-based reconstruction, and we can see that it blurs the images. So the 1.5 millimeter resolution data, as I said, we acquired and kind of showed to show that the method works, because there we could have a reference. But clinically more typical are 1 millimeter resolution scans in this kind of like T1 weighted sequences. And yeah, and so this slide is kind of to show that we can also acquire and use our data at 1 millimeter resolutions, which is more challenging regarding scan time. So we also tried different scan times to kind of see the image quality scan time trade-off. Now, one question you could ask is, okay, what can these MPN-rich images be used for? And first of all, they can be used for what we call tissue nulling. So the main tissues of interest in neuro MRI are white matter, gray matter, and CSF. And we can see here, for example, in the white matter nulled image that the white matter region is black. And so therefore the contrast in the gray matter is higher. So, I mean, we have more signal from the gray matter. And so this way we could see anomalies in the gray matter better. And the same is for the other nulled images. Additionally, what I mentioned before, we can get quantitative T1 maps that we can fit from these multi-contrast images. And tissue nulling as well as quantitative T1 maps can then be used for biomarker discovery, for example, in the context of Alzheimer's, which my project is focusing on. And I mean, the project that I'm kind of part of. And last but not least, we can also synthesize a clinical T1 weighted contrast, which is usually acquired with a sequence called MP-RAGE. So you now also understand what MPN-RAGE stands for. Like in our case, N is 10, so like 10 different T1 weighted images. And as you can see here, we can also get like a coronal and sagittal view of the brain, stacking the slices that we reconstructed with the INR. To conclude, we propose a method for a highly accelerated multi-contrast MRI, and we combine complementary undersampling and a joint INR reconstruction to leverage shared anatomical information across contrasts. Our method is self-supervised and scan-specific, which means that no large training data is needed, which is good because in the context of multi-contrast MRI, such big data sets do not exist. And additionally, this makes our method also more robust if you want to apply it to completely different data sets. So in the meantime, our method has also been applied to actually the multi-echo T2 star data that Julia was mentioning before. And yeah, this kind of shows that from scratch, without kind of training it again, you can just use it for other data too. And yeah, the results we get is kind of that with prospective accelerations up to R20, we get a promising image quality, and this allows for clinically feasible scan times, for example, in the case of MPN-RAGE for minutes 22. And now as a next step, as I mentioned before, I'm part of, it's called Predictum, is like a European IHI grant project that acquires a big data set as part of a study to focus on early Alzheimer's detection. And in this framework, we're now going to acquire this like accelerated MPN-RAGE data that we can then do more analysis on. Finally, I want to thank everyone from my lab and also from my team at GE Healthcare, where I'm doing an industry PhD, for the support in this project, and I'm happy to take questions.